3:30 in the morning. A man is sitting in a chair he has been sitting in for 6 hours, in a room with no windows, watching a number that has not moved. The reactor in front of him is off. He shut it down himself before midnight on schedule for planned maintenance, and everything about it went the way it was supposed to go. Every control rod is fully inserted, the chain reaction is stopped, the turbine is stopped, the plant is selling nothing to anybody, and the core on the other side of that wall is still hot enough to destroy itself. And it will be hot enough to destroy itself tomorrow, and next week, and next year. So he sits there, not because anything is wrong. Because if the water stops moving through that core, nothing he can do afterwards will help, and there is no switch in that room or anywhere else that makes the heat stop. Ask anybody what a nuclear operator is afraid of, and they will tell you a runaway reaction. Something going critical. It is the opposite. Stopping the reaction is the easy part. It takes seconds, and it is automatic. What nobody can stop is what happens afterwards, and afterwards lasts years. So the questions: if the reaction stops in seconds, what exactly is still making heat 6 hours later? Why does a power station need electricity from somewhere else in order to stay safe? And what happens on the night it does not get any? Why did the worst nuclear accident of this century happen at reactors that had already shut down correctly and automatically? Why is there a swimming pool at every one of these plants that is more dangerous than the reactor? And why, in the whole documented record, are two of the incidents that stopped the cooling water a rat and a man's elbow? Today we go through one night in a control room, in order from the moment the rods go in to the moment the shift changes, and then out to the pool at the top of the building that nobody photographs. If you want to understand the machine that runs your kettle and cannot be turned off, subscribe now so you do not miss this one or the ones after it. And we start with the thing that stays behind after the reaction stops, because everything else in this video is a consequence of it. Shutting a reactor down is genuinely fast, and it is worth being clear about that because it is the part people get wrong in the other direction. The control rods drop or drive into the core, they absorb the neutrons that keep the chain reaction going, and the fission stops within seconds. That system works. It is gravity-assisted. It works without operator input, and on the day of the earthquake in Japan, every reactor that was running shut itself down automatically the moment the ground moved. Not one of them failed to stop. That is not where the accident was, because when the fission stops, the core does not go cold. It goes to something like 6 or 7% of the heat it was making while it was running. 6% sounds like almost nothing. Now think about what it is 6% of. A large power reactor produces thermal power in the region of 3,000 megawatts. 6% of that is around 200 megawatts of heat, sitting in a sealed vessel, with the reaction stopped, with nobody able to reduce it. That is the output of a decent-sized power station in its own right, and it is being produced by something you have just switched off. So what is making it? Not fission. Fission has stopped. What is making it is the wreckage of fission. Splitting uranium leaves behind hundreds of different lighter elements, and a great many of them are unstable. They decay. They throw out particles and radiation on their own schedule, one after another, and every one of those events deposits a little energy as heat in the fuel around it. It is not a reaction you can stop by pulling something out, because nothing is sustaining it. It is the fuel finishing what was already started inside it, and it fades, which is the one piece of good news in this entire subject. From 6 or 7% at the moment of shutdown, it falls quickly, down to something around 1.5% within an hour, and to a fraction of 1% within a day. The curve drops steeply at first and then flattens out into a very long tail, which produces the two facts that define everything about operating these machines. The first day after shutdown is the dangerous one, and the tail never quite reaches zero. Put those together and you get the sentence that the whole industry is built around. There is effectively no way to shut a nuclear reactor all the way down. You can stop the reaction completely. You cannot stop the heat. So the cooling has to keep running after the shutdown in some form, or the fuel heats past its melting point and melts. And it is worth being blunt about what that means, because the industry's own phrasing is blunt. Molten fuel can burn through the vessel and the barriers around it and release radiation into the outside world, which is why the man in that chair is still there at 3:30, 6 hours after doing everything correctly. He has not failed at anything. The reactor did what it was designed to do. What he is now doing is the other half of the job that most people do not know exists. Sitting with a machine that has been switched off and is still dangerous, making absolutely sure that water keeps moving through it on a curve that will take days to become comfortable and years to become irrelevant. And it is worth knowing what he is doing with those 6 hours because it is not sitting still, it is a slow, deliberate walk down a curve. Bringing a reactor to a genuinely settled condition is a procedure, not an event. The water has to be kept moving. The pressure has to be brought down in stages. The temperature has to be walked down rather than dropped, because thick steel cooled unevenly cracks, the same problem as a furnace lining, arrived at from the opposite direction. There is a target condition with a name, cold shutdown, and reaching it takes days rather than hours even when everything goes correctly. And in the middle of that, he is doing the thing nobody outside the industry associates with a nuclear plant at all, which is watching pumps, flow rates, bearing temperatures, current draw on a motor, whether the standby pump was tested this month, whether a level in a tank is moved by an amount that means anything. It is the same work a man does in a waterworks or a refinery, and it is being done for a completely different reason, because on the other side of that wall there is a quantity of heat that will keep arriving whatever anybody decides. And this is the point in the story where a normal person asks the obvious question, and the answer to it is the whole rest of this video. If the reactor is off and it still needs cooling, what is running the pumps? Because the plant is not generating anything. Its turbine is stopped. The thing that normally produces the electricity for the site is the thing that has just been shut down. So a power station, at exactly the moment it becomes most vulnerable, becomes a consumer rather than a producer, and it needs power from somewhere else in order to remain safe. So walk the chain of things keeping that core cool because every single link in it runs on electricity. The pumps that push water through the core are electric. The pumps that carry the heat away to the sea or the river or the cooling towers are electric. The valves are electrically actuated. The instruments telling the operator the water level and the temperature are electric. The lights in his room are electric. Take the electricity away and he does not lose one of those. He loses all of them at once, including his ability to see what is happening. And there is a second reason all of it is electric, which is not obvious and which makes the problem worse rather than better. A reactor is a sealed pressure vessel. You cannot reach into it, you cannot look into it, and you cannot cool it by opening something and letting air at it. Everything that happens to that core has to be done through pipes, by pumps, from outside, and every one of those is a machine that needs power. There is no manual option. Nobody can turn a hand wheel and cool a reactor core. The only access anybody has to it is electrical, which is why the normal arrangement is to take power from the grid, from outside the plant, and why the industry has a specific name for losing it, a station blackout, and it is not treated as an inconvenience. It is one of the scenarios these plants are designed against most carefully, because it is the one that removes every active safety system simultaneously. So there are layers, and the layers are physical rather than clever, a second grid connection from a different direction, then diesel generators on site, then batteries, then in the newest designs, water held high up that can fall through the core using nothing but gravity. The diesels are the layer everybody has heard of and the layer that matters most in practice. Large emergency generators, tested regularly, sized to run the cooling pumps and the instruments for as long as it takes. They start automatically when the supply drops. And notice what has just happened to this machine. The safety of a nuclear reactor now depends on a diesel engine starting, exactly like a hospital in a power cut. There is nothing exotic in that link at all, which is precisely why it is the one that fails. And behind the diesels sit the batteries, for the hours when even the diesels are gone, and they are a smaller comfort than they sound. Batteries can hold instruments alive and run some valves. They cannot run large cooling pumps for long, so the battery layer is not a way of staying safe. It is a way of staying informed and keeping some options open while somebody restores something bigger. Which means the honest description of the defense is a countdown with several stages, and every stage buys hours rather than solving anything. And there is one layer that is not electrical at all, which is the reason the first hour after a shutdown is survivable. The plant is full of hot water and steam at the moment the reactor stops, and some designs use exactly that. A turbine-driven pump takes steam from the reactor itself and uses it to drive the pump that feeds water back in. No electricity anywhere in that loop, the reactor's own residual heat, becomes the thing that cools it. It is elegant, and it works for hours rather than days, because eventually the pressure falls and the pump has nothing left to turn it, which is the pattern in every one of these systems, and it is worth stating plainly once. Nothing here is a solution. Everything is a delay. The steam pump buys hours. The batteries buy hours. The diesels buy as long as they have fuel and cooling. Each layer exists to hand the problem to the next one, and the only real solution is that the decay heat curve comes down far enough that ordinary means are sufficient. The plant is not being saved by these systems. It is being carried by them down a curve that takes days. There is one more link, and it is the one nobody thinks about because it is not a machine at all. The heat has to go somewhere. You are moving it out of a core, so it has to be dumped into the sea, a river, or the air through cooling towers. That means heat exchangers and seawater pumps at the water's edge. And that equipment is at the water's edge because it has to be, which is a completely reasonable engineering decision that turns out to matter enormously, and we are about to see why. And now the thing that makes all of this heavier than it first appears, because it is not only the reactor that needs the water. Near the top of the reactor building at these plants is a pool. Used fuel comes out of the core and goes into it, underwater, because used fuel is still producing heat and still needs shielding. It stays there for years, typically around 3 years before it is cool enough to move to dry storage, where air convection alone is enough. And while it is in that pool, the water in it is circulated by electric pumps through heat exchangers, exactly like the core. And the reason that pool exists at all is worth a beat, because most people assume used fuel is waste that gets taken away. It cannot be taken away for years. When fuel comes out of a core, it is intensely radioactive and intensely hot, and both of those fall on the same kind of curve as the reactor's own decay heat, steeply at first and then very slowly. Water does 2 jobs at once in that pool. It carries the heat away, and it is a shield, because a few meters of water stops the radiation that would otherwise make the top of that building uninhabitable, which produces something genuinely uncomfortable when you look at the whole site. The reactor is inside a containment structure built to hold pressure and contain radiation. The pool, at many plants, is not. It sits in the reactor building outside the containment, near the top, holding years of accumulated used fuel. And it depends on the same electricity as everything else, so the plant's most protected object needs cooling, and so does an unprotected swimming pool above it, and both of them need the same pumps. So back to the man at 3:30, and now you can see what he is actually watching. Not a reactor, a water level, a temperature, and a set of pumps, all of which exist downstream of an electricity supply he does not control. His shift is quiet, nothing is happening. And the entire content of his job tonight is that nothing continues to happen to a chain of ordinary equipment, any link of which would turn a switched-off reactor into an accident over the following days. And once a year or so, somewhere in the world, one of those links goes. Usually it is caught in minutes, and nobody outside the plant ever hears about it. Occasionally it is not. And on one afternoon in March, on a coastline in Japan, every single layer we have just described was removed inside about an hour. Not by a design flaw, and not by an operator, and not by the reactors failing to shut down, because they shut down perfectly. And before we go there, one thing about that afternoon that matters for understanding it properly, because the reactors that ended up in the news were not the only ones affected. 11 reactors along that coastline shut themselves down when the ground moved. 11, 4 at one site, 3 at another, 1 at a third, and 3 at the site whose name everybody now knows. Same earthquake, same sea, same afternoon, same physics, and broadly the same generation of engineering. What happened to them afterwards differed completely, and the difference had exactly one cause. The earthquake came first, and the reactors did exactly what they were built to do. Every unit that was running inserted its rods automatically and stopped fissioning. The grid connection was damaged by the quake, which is a scenario the plants are designed for, so the emergency diesel generators started and took over the cooling. For roughly the next hour, at 11 reactors across several sites on that coast, the cooling water was moving and the situation was under control. If the story had stopped there, none of us would know the name of the place. Then the wave arrived, and what it did was not to break the reactors. It went for the ordinary equipment. The generators were flooded. 12 of the 13 backup generators on the site were disabled. The batteries that were supposed to cover a blackout were flooded too. The electrical switchgear that distributes power around the plant was disabled. And the heat exchangers at the water's edge, the ones that had to be at the water's edge in order to dump heat into the sea, were inundated as well. Read that list again and notice what is missing from it. Not one item on it is nuclear. A diesel engine in a basement, a bank of batteries, a switchboard, a pump at the shoreline. Every single one of those is equipment you would find in a large factory, a hospital, or a port, and every single one of them was taken out by water in the same few minutes. The reactors were, in the industry's own summary, robust seismically and vulnerable to the tsunami, and what was vulnerable was the electricity, not the reactor. And there is one more thing on that list worth pausing on, because it is the one that had nothing to do with water reaching a basement. The switchgear. A switchboard is not a safety system in anybody's mind. It is the thing that distributes electricity around a building, the industrial version of a fuse box. Lose it, and you can have working generators and working pumps, and still have no way to connect one to the other. Which is why, later in this video, an animal in a switchboard is going to stop the cooling water on the most closely watched nuclear site in the world. Power was lost at about 3:45 in the afternoon, roughly an hour after the shutdown. At that moment, on the decay curve from Section 1, the cores were still producing around 1.5% of their full thermal power. 1.5%, with no pumps, no instruments, no switchgear, and no way to dump heat to the sea. And nobody in those control rooms could make that number smaller. It was going to come down on its own schedule over the following days, and until it did, the fuel needed water, and there was no way to move any. And the comparison that tells you everything is on the same coastline on the same afternoon. At 8 of the 11 reactors that shut down along that coast, power was available from the grid or from generators that survived, and the residual heat removal pumps ran. Those 8 units reached cold shutdown within about 4 days, with some problems, and are a footnote. 3 units lost their power. Those 3 lost the ability to cool, the fuel melted, and the world learned the name of the site. And there is one more thing about those 8 units that is easy to skip past and is the most reassuring fact in this video. The summary says they achieved cold shutdown within about 4 days, with some problems. Some problems, which means those crews were not having a quiet afternoon either. They had lost grid power, they were running on diesels, they had damage around them and aftershocks continuing, and they got their reactors to a settled condition anyway. That is the system working under an extraordinary load, and nobody has ever made a documentary about it. Same earthquake, same reactors shutting down correctly, same physics. The only variable that mattered was whether the pumps had electricity. That is the whole lesson of the accident, and it is why this video exists. The nuclear part of a nuclear plant behaved as designed throughout. What failed was a diesel engine's location, a switchboard's location, and a pump's location, decided decades earlier by people who were not thinking about a 15-meter wave. And then, because the site could not be cooled, the work of the following weeks was not about reactors either. It was about restoring heat removal and coping with used fuel ponds that were overheating because their pumps had stopped as well. Weeks of focused effort by people on a contaminated site, whose entire task was to get water moving again through things that had been switched off since the first minute. Cold shutdown condition was finally declared in the December of that year. 9 months. And there is a detail in that recovery which puts the whole subject in proportion better than any diagram could. Pouring hundreds of tons of water a day over the reactors is what the operator was still doing years afterwards, not restarting anything, not repairing anything. Water in continuously every single day, because the fuel in there was still producing heat and there was no longer any normal system left to remove it. That is what the tail of that curve looks like once the machinery designed to handle it is gone. It looks like a hose running for years. And here's where the story stops being about a tsunami, because 2 years later on that same site, the cooling stopped again, not from an earthquake. A rat got into an electrical switchboard and caused a short circuit. That power cut shut down the cooling systems for 4 used fuel ponds. The reactors themselves were unaffected. Cooling was restored progressively over the following day and a half. The pool temperatures stayed within safe limits throughout, and the operator was criticized for taking 3 hours to tell anybody it had happened. A rat. Not a design flaw, not a decision, not a failure of anybody's judgment. A rat. On a site being watched by the entire world at the most scrutinized nuclear facility on the planet, with every lesson of the accident freshly written down. And this is not a story about incompetence, which is the easy and wrong conclusion. It is a story about what the chain from Section 2 actually looks like in real life. Somewhere in that chain is a switchboard in a building, and a switchboard in a building is a thing an animal can get into. Nothing about the physics of the reactor protects it from that. And in the same year, on the same site, there was another one that is even smaller and even more instructive. A worker was carrying out inspections and passing along a narrow aisle between switch panels. He bumped a switch. The cooling for one of the melted reactors stopped, and it stopped for nearly an hour until a backup pump came in. There was enough water in the reactor, the temperature did not rise, nothing was released, and the operator afterwards acknowledged that some other key switches were in similarly tight locations. And what makes that detail worth telling is not the mistake. It is the sentence the operator added afterwards. They acknowledged that some other key switches were in similarly tight locations, which means that at the time it happened, on that site, there were several more places where a person walking past could do the same thing, and nobody had noticed, because nobody had done it yet. Every one of those aisles had been walked down thousands of times without incident, which is exactly the reason it was not on anybody's list. Sit with the shape of that for a moment, because it is the most honest thing in this entire subject. Not sabotage, not fatigue, not a wrong decision under pressure. A man walking down a corridor that was too narrow, doing his job, touching something with his body that he did not intend to touch. And on the other side of that switch was the cooling for a reactor core. The consequence and the cause are not remotely the same size, and they never are in this industry, which is also why there was a backup pump and why it came in and why the temperature did not move. Because the industry knows this about itself. It does not design around competent people doing everything correctly. It designs around a corridor being too narrow and an animal getting into a cabinet, because those are the things that actually happen. Numerous systems and backup emergency core cooling systems exist specifically so that only the failure of all of them can produce a severe accident. The rat and the elbow were both absorbed, and that tells you what the modern designs are trying to do, which is to take the electricity out of the chain altogether. Some newer plants hold large pools of water high up in the building so that gravity alone can feed the core for a long period with no generator and no pump. Some designs use a large, low-pressure vat of liquid metal in which natural circulation carries the decay heat away by itself. Others can drain their fuel into a passively cooled tank. All of those are attempts to answer one question: what if there is no power, and no diesel, and nobody in the room? And there is one more thing about the human side of this that separates it from every other job in this series, and the people who do it will tell you about it first. Nothing happens. That is the job. An operator can work an entire career without a single event anybody outside the building would call an incident. The skill being exercised is not reacting under pressure. It is remaining genuinely attentive to a number that has not changed on the 4,000th night when every previous night taught you that it never changes. Vigilance with no stimulus is close to the hardest thing a nervous system can be asked to do. And that is exactly why the industry does not rely on it, and says so openly. The rat did not need to be anticipated by anybody. The backup pump came in after the man bumped the switch, without a human deciding that it should. The entire structure is built on the assumption that the person in the room will at some point be tired, or distracted, or simply have an elbow in the wrong place, and on the principle that this must not be the thing that decides the outcome. In this industry more than any other, the engineering is designed around the person failing. So let us close the four things this night is built on. The reaction stops in seconds and reliably. The heat does not stop at all. It falls steeply for a day and then trails away for years, and nothing anybody does can make it fall faster. Removing that heat requires electricity, which makes a switched-off power station a consumer at its most vulnerable moment. And the layers protecting that supply are a second grid line. Diesel engines, batteries, and in the newest plants, gravity. Every one of those is well engineered, and the record proves it. 8 reactors on that coastline kept their power and are a footnote in a report. But look at what actually interrupted the cooling water in the documented cases, and none of it is nuclear. A wave that reached equipment in a basement, an animal in a switchboard, a man's body in a narrow aisle. The reactor has never been the thing that failed. The thing that fails is always something ordinary, somewhere in a building, attached to the electricity. Which is why he is still in the chair. Not because he can cool the core with his hands. Because somebody has to be the thing that notices that the level has moved slightly, that a pump is drawing more current than it did an hour ago, that a diesel failed its test last week and nobody followed it up. On a good night, that is 6 hours of watching a number that does not change, and then handing over to somebody who will do the same. And there is one more thing he is doing that does not look like work and is the most valuable thing in the room. He is keeping a picture in his head, not a reading. A picture of the whole plant as it was an hour ago and as it is now, so that when something moves, he knows whether it has moved for a reason. Nobody can hand that over on a clipboard. It is why shift handovers take as long as they do, and why the first hour of any shift is the one where an operator is least useful, because he is rebuilding a model of a machine he cannot see. And there is a part of this job that outlasts the plant itself, which is the strangest thing about it. The pool near the top of the building still has years of used fuel in it, and it will need cooling and shielding for years after the reactor is closed for good, which means that when a nuclear plant stops selling electricity forever, when it is decommissioned, when the turbine hall is empty, somebody is still on shift, watching pumps, in a building that produces nothing at all for decades. So the next time you switch something on, that is part of what you are buying, and it is not on the bill. Not fuel and not a turbine, a commitment made by somebody long before you were a customer, that for as long as that fuel exists there will be water moving over it and a person in a room watching that it still is. The electricity arrives in a fraction of a second and disappears. The obligation it created lasts longer than the career of everybody who built the place. And there is a version of that obligation that is easier to picture, and it is happening right now in dozens of countries. Reactors that were switched off years ago still have staff, not construction crews, operators watching cooling systems, monitoring pools, doing rounds in buildings where the turbine hall is silent and nothing is being sold to anybody. Some of those plants will be in that condition longer than they spent generating. The reactor's working life is measured in decades. The obligation it leaves behind is measured on the same scale, and it starts the day the machine stops earning. And that is the answer to the question in the title, and it has almost nothing to do with atoms. A nuclear reactor cannot be switched off because switching off is not a state that exists for it. There is running, and there is shutdown and still being cooled, and the second one goes on for years. There is no third option, and there never has been. What people call switching it off is not an ending at all. It is the beginning of the part that cannot be stopped, and somebody has to sit with it. Would you sit that shift? 6 hours in a windowless room, watching a number that does not move, on a machine you have already turned off? Tell us in the comments. Honestly, not bravely. And if this was interesting, subscribe and give it a like. It helps us make more stories about the machines that cannot be allowed to stop, and the people who sit with them. Next time, the furnace that has been on fire for 21 years, where letting it go cold destroys it completely. And why the enemy of a blast furnace is not heat.